again. This is Dr. Joel Shertok, President of Process Industries Consultants, a chemical engineering consultancy located in Newark, Delaware. For today's podcast, I'd like to kind of expand some of the things I talked about during the last podcast we did, talking about both the idea of mass transfer and chemical kinetics, talking about reactions that occur in two phases, and then make a transition to a little bit that we talked about last time, which is good chemical plant hygiene and good operations control. So last podcast, if you recall, I discussed how the regime between chemical kinetics and mass transfer is very critical in maintaining a low PONC, a low price of nonconformance. There are many factors that go into an interaction between mass transfer and chemical kinetics in a two-phase reaction. Typically, it's gas-liquid, but it could be liquid-liquid as well. Of importance is the size of the bubble. The bigger the bubble, the worse your mass transfer is going to be. It's all governed by the ratio of surface volume to surface area. You want a high surface area to volume ratio because this gives you the maximum amount of mass transfer. Typically, what industrial concerns use are small holes made in a copper pipe called a sparger. The smaller those holes are, the better off you're going to be. And commercially, you can find spargers today that actually produce a fog. The holes are so small that you don't see bubbles anymore, you see a fog instead. And this, because of the high ratio of surface area to volume, gives you the mass transfer that you desire. What's the trade-off? Obviously, the smaller the hole, the greater the pressure drop to get the air through the sparger hole. But the trade-off is superior mass transfer, and therefore the ability to make your product with a minimum of loss toward byproducts, and again, a decreased price of nonconformance. What's often missed is the importance of mixing. Mixing tends to be an afterthought. You typically specify, propeller agitator, and you do, maybe 240 RPM and blah, 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 and you figure you're set. But that is not so simple. You have to think about what's the viscosity of your liquid? What's the ratio? What is the viscosity of your gas? How the two viscosities interact with each other? If you choose incorrectly, you can do all the mixing in the world and it will do you no good at all, and you've been mystified about why your reactor is misbehaving. So let's consider an example from my past. We had a simple mixing operation, no reaction, simple mixing operation. And we're mixing peracetic acid in with another organic solvent. And no typical propeller agitator, no problems, blah, 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 blah. In the lab, we were able to achieve mixing in something like 30 seconds. No problem at all. I mean, they're both equally miscible. Not a challenge at all. But in the plant, for years, that mixing took 3-4 hours. And nobody understood what the problem was. You had to mix, and you had to mix, and you had to mix to get those two liquids that were not two phases. They were actually miscible liquids into solution. So what do you suppose the problem was? In the lab, you had a relatively small, 1,000-liter beaker, 1 liter. You had a typical propeller stirrer from the lab. You can buy them from Cole Palmer, no problem at all. And when you poured in the peracetic acid into another organic, it mixed right away. Not a problem at all. 30 seconds, you were done. Same situation, again, as I said, in the plant. Took forever. Made no sense. Why would it take forever in the plant situation? So what we did is we did the obvious thing. We went out to the plant and we observed what they were doing. Now, those of you who have seen a typical mixing operation know that in the middle of the reactor, you typically form a vortex. The propeller stirring causes a vortex, and since you typically center the propeller in the reactor, you see this nice vortex forming in the middle of the reactor. Well, that's fantastic. What we saw when he went to the plant is because the reactor was, of course, a standard-sized reactor, the operators were not putting the peracetic acid into the vortex. They were pouring it down the side. In other words, how far can your arms reach, after all, when you're putting in things manually? And so I poured it down the side, and it took forever to mix. So he said, aha, let's go back to the lab and simulate what they're doing in the plant under the same circumstances. So same 1,000 milliliter, 1 liter beaker, same Cole-Palmer propeller agitator, nothing changed. And what we did is we took the peracetic acid and we carefully poured it down the side of the beaker rather than putting it into the center, as you intuitively do. What happened? The peracetic acid went down the side and layered down at the bottom. It was heavier. Peracetic acid's heavy. It basically layered at the very bottom of the beaker. And once it did that, you had to stir, and you had to stir, and you had to stir to get that peracetic acid into the solution, because it's no longer in the vortex. You had to do it almost indirectly. The swirling liquid above it had to encourage the mixing of the two phases. And it took 45 minutes, completely simulating what the plant saw. So we knew what the problem was. Now, how do you solve the problem? Well, you put the peracetic acid in the middle of the reactor, into the vortex, like you should. Well, how do you do that? Well, you go down to Home Depot and you buy a metal chute, stainless steel, plastic, your choice, $12. Chutes maybe 4 feet long, and maybe, a nice concave view, maybe a foot or so. And what you do is you take your Home Depot chute and you put your peracetic acid down the middle, and it goes into the vortex, and mixing takes 30 seconds. So all it took to solve a problem that bedeviled the plant for years, all it required was a trip to Home Depot and a $12 solution. And you think of all the time you saved in wages, all the fixed costs, all the period costs that you avoided by a trip to Home Depot. And that's why I say sometimes the most obvious solution escapes people, because you don't see the forest for the trees. And if you're working in a chemical plant and you're in the operations area, keeping your eyes open to the obvious can sometimes save you millions of dollars. Think how much time you saved each time you made a batch. Instead of a 2-hour cycle time, it was now down to 5 minutes. Well, you can do the mathematics yourself and see that comes out to tens of thousands of dollars for every run, and basically think that over a year. What a way to avoid punk, and no cost at all when all is said and done. So that's an example. What other examples do we see in a plant environment that can bedevil the chemical engineer? We talked a little bit about good plant hygiene. We used last week the example of not checking your instrumentation to make sure that a reading that you thought you saw was an actual reading that the tank actually saw. Here's an example. So most chemical plants have a formal training program, right? You have manuals, you have binders, you have everything, and the operators go through a rigorous training, or so you think. The reality is most chemical operators learned how to do their job from their supervisor, or Charlie on the line who's been there 20 years, or somebody who inculcates them with the plant folklore, the way things are really done, as opposed to the way the SOPs lay them out. And that is incredibly maddening, because what it means is that you have a shift of maybe 4 or 5 different operators running the plant. Every time the shift change, instead of following SOPs, you have plant operators who are running the plant the way they were taught to run it by Charlie. And Charlie is a real smart guy. He has 20 years on the line. He knows all the quirks. He knows all the workarounds. The SOPs, well, that's interesting, but when all is said and done, Charlie thinks his experience is far, far better than what the SOPs lay out. So one example is one of the companies I worked for was a filtration company. They made membranes that are used for filtration operations. And one of the main QCs, cheap QC, on a filter coming off the line is something called a bubble point. You basically apply nitrogen under pressure to a membrane in a fixed holder. And when you see bubbling, i.e., what's called the champagne effect, you see bubbling of nitrogen out of the membrane, that's called your bubble point. And the bubble point can be related to the membrane pore size. And of course, the membrane pore size is directly related to the filtration efficiency of that membrane. In principle, your bubble point should always be the same, assuming that your manufacturing operations haven't varied. There's a set SOP for doing the bubble point. But unfortunately, most of the operators who tested their membrane were trained by Charlie. And this was the way to do bubble point. Never mind SOP, Charlie showed me how to do it. And you could tell when a shift change occurred because the bubble point either take a step upward or a step downward. Not wrong, just a different methodology. And it's maddening because it shouldn't happen. There's a standard SOP, and the way the bubble point's determined should follow that SOP. But it's very, very, very hard to overcome ingrained folklore. Now, folklore has some good uses. You do not go against an operator in your plant without very careful consideration. Most inexperienced engineers will come on saying, well, hell, I got my Bachelor of Engineering degree, and I damn well know how this process should run based upon my coursework and whatever training I got from the front office. You very rapidly learn that if you go in with an experienced operator who has his 20 years in, and he says not to do something, you need to consider where he's coming from and why he says that. Now, sometimes it's just based on folklore, or somebody, did something 15 years ago and it didn't work out, and that's fine. You can kind of apply your engineering knowledge. A lot of times, that supposition, that assertion, is based on some real solid operating experience. And you need to pay very careful attention if you want to go against that. Because what the operator may do is he'll do exactly what you tell him to do, and you'll wind up looking incredibly foolish. So the idea of understanding the way a plant runs, the idea of SOPs, the idea of how an operator runs the plant as opposed to the way the SOPs run is something you really have to take into account. In this era of ISO, in this era of GMPs, in this ISO of much, much tighter process control, this becomes an issue. Because if you're ISO certified, it means that you must run your plant according to your procedures. Before the ISO days, yes, you had SOPs, and people kind of followed them. But if they didn't, there was really no way of documenting that, and that's just the way things were. Today, if you get audited and they find that your operators are not following your SOPs, they'll pull your ISO certification, which is very, very embarrassing. Now, what does that mean? When people certify against ISO, they think that the more elaborate, the better. Boy, if I have this really elaborate system of procedures and processes, I am going to have a great ISO plant. And the truth is, nothing is further than the truth. You talk about a way to generate punk in your plant. I certify your plant via ISO using complex operating instructions. No, because once you write them down and once you're certified, you've got to follow them. And if they are incredibly complex, you'll lose your shirt because nobody will be able to follow them, and you'll be accumulating more and more punk in your plant. The reality is, if you're doing ISO, your operating instructions should be no more complex than you need to make that plant run. The simpler, the better. There is no reward in the world of ISO for making a complex operation, and you'll be tripping yourself up. What other issues do you have to kind of consider in avoiding punk in a plant? Well, believe it or not, ESH, health, safety, and environmental, is probably the most important aspect of this. When I first started working in chemical plants in the mid 70s, safety was important, but not really important. The important thing was to get product out the door. That was the religion. More product, more profit, everybody's happy. I started, as I said, I started working for Union Carbide in late 75. What changed Carbide's attitude was a really horrific accident that happened maybe 6 months before I came on board. Many of you who are in the chemical industry know about lockout tagout. In other words, anything that has a chance of being operated via electrical motors is locked out, tagged out, so it cannot be started while maintenance people work on that. Carbide in the mid-70s, 73, 74, of course, didn't have that because no industry had that. And so happened that an operating employee was inside a paint blender doing preventive maintenance, no problem. But nobody knew he was in there. And an operating supervisor walked on by, saw that this machine was not running, and he said, geez, why is this machine running? We're losing productivity. And hit the on switch. And you can guess what happened. You had the only good thing about it is the guy was killed pretty fast. But you destroyed a guy. You made blended operator, basically. And that woke Carbide up. That did woke Carbide up as the importance of health, safety, and environmental. You don't want that to happen in your plant. You talk about a punk. And again, there's always this tension. We got to get this piece of equipment. We got to get this piece of equipment. We got to get this piece of equipment. There's a tremendous pressure. Get it done, get it done, get it done. If you succumb to that, you will be sorry. You will have a severe accident, and you'll have a very, very hard time explaining why you possibly circumvented plant procedures just to get productivity out. So consider that. Another example from my own background. One of the companies I work for, they make toilet seat covers, the ultimate commodity. Those of you who are forced to go to a gas station for a quick trip, they almost all have toilet seat covers on their toilet seats. It's a commodity business my company was in. The toilet seat covers, the machines that made them, looked like they came out of Charles Dickens. They were 1940s, 1950s technology, no safeguards, no interlocks. But again, it was a commodity product. You're selling for pennies by the hundreds. Get it out was the key. And one day, an operator lost track of what he was doing. And he put his hand into the machine while it was feeding. And he was lucky. He just got a couple of bad injuries. He didn't get his hand crushed like he could have. So I was in charge of safety in addition to R&D. And I said, no, this can't go on. You can't use Charles Dickens era equipment, although it's a commodity product. And I put my foot down. I made them retrofit all their machines using interlocks, safeguards, things of that nature. So if somebody put their hand too near an active piece of equipment, it would automatically shut down. But I got tremendous opposition from management. They said if the capital cost is too much, it's a commodity product. And one of the senior managers said, hey, Joel, just tell them, don't do anything unsafe. And he was not a mean guy. He was not a cruel guy. He was a wonderful guy. His grandfather founded the business in 1888. But he had that mentality that, no, we got to get stuff out the door. And I did not win any friends in that company by making them put those safety interlocks on. But I knew it was my responsibility as the safety guy for the plant to make sure that, there was not a repetition. Sometimes you don't know things are going to happen. Sometimes it's by the best efforts that you make, there's issues. But you, as a practicing operations person, need to make sure that your operation is as safe as it possibly can be. And sometimes you've got to put up with, dirty looks from the management because you cost them, quote, time and money. What's the old saying? There's never time to do it right, but there's always time to do it twice. When it comes to chemical work, yeah, that's semi-okay. But if it's people and people's lives, no, that's not okay. And you, as a practicing professional, have to put your foot down because somebody being injured is the ultimate punk for a plant. So this week we have covered concepts in mixing. We've covered concepts in QA. we've covered concepts in SOPs, and we've covered concepts in plant safety. That wraps up this particular topic, and next week I'll be discussing some additional issues with chemical engineering and operations. Thank you for your time.